Okay, so let's begin. Okay, so today let's focus on a few questions. Is the audio working? Marco, can you hear me? Okay, a little bit soft, huh? Let's try to make it a little bit better. Volume. Let's increase the volume a little bit. How about now? Okay, good. All right. So first of all, I posted another Harold note about cross products, fractal dimensions, gamma functions. All of this is outside class, but just for your background. Now, today, let's begin with a relatively easy question. So making sure you guys know how to use Maxima. Now, I realize that on some of your computers, Maxima was not working. We'll try to get it to work over the next day or two. Hopefully by next week at the latest, Maxima will be working. Okay, so so we'll try to make sure that that happens. In particular, Maxima hopefully will be working for your exams. So we'll make that happen. Can I ask for, let's see, who did this? Yeah, so Yue to come and help explain the solution for question number 3. All right, Young. So Young is coming and he'll explain his solution. So to take a look at question number 3, this was a relatively straightforward question, but it asked you to consider the cone. So a cone with base of radius 5 on the xy plane. Z equal to 0 is the same as xy plane. Vertical axis along the z axis and height 12. Right? So visually, Young's solution looked a little bit like this. This is the cone, right? Now, the question asked you to plot this in a variety of different ways. So using cylindrical coordinates. So when the radius is a function of the z-axis and the theta coordinate, so the height and angle. So here, the challenge in doing this is to find the minimum and maximum values of z, minimum maximum values of theta, and find the appropriate function, f, as a function of this, right? And so that's the conceptual part of question 3. But then making sure you know how to do this on Maxima. So first of all, the command is wx draw 3D. If Maxima is working on your computer, so it's wx draw 3D, then cylindrical coordinates. And then the function that he's using is 5 minus 5 times z by 12, comma z, comma, z going from 0 to 12, theta going from 0 to 2 pi, right? So the radius, once you fix the height, z, and once you fix the angle, then the radius of the surface is going to be a constant. It's independent of theta, because in this cone, the height is the same regardless of what the angle is, right? So in cylindrical coordinates, this function is 5 minus 5z over 12, and theta going from 0 to 2 pi, right? Okay, so look, it looks quite nice and smooth over here, this cone, right? Now, if you try drawing it implicitly, okay. So, by the way, when I ask you to repeat this, just explain a little bit why this is the function and the ranges of z and theta. Okay. Actually, let's do a short explanation right now. Okay. Yeah.
就是我这个函数写出来，它是5减去5乘上一个 c 除一个12，就是我考虑的是，就先在那个 xc 平面内。然后写出就是一个直线嘛，写出一个直线的一个表达式，就是它那个斜过来的那个表达式。然后它那个后面的西塔就是让它转，西塔就是让它转1周，就让这个斜线转1周，然后就变成了这样子的一个形状，一个圆锥。
Okay, so if you know how to draw it explicitly, either in cylindrical coordinates or something else, you should do it. You'll get a smooth curve. But sometimes you don't know. Like sometimes someone has just told you that the function has some formula. So in this case, the formula that Young used is x square plus y square minus z square scaled by this quantity plus 25 by 3z minus 50 is equal to 0. So basically, it's going to be some function f of x comma y comma z equal to 0, right? In this case, sometimes the function that's given to you is just some function in x, y, z equal to 0. And it may be hard, like you may not know how to write this as z is equal to f of x comma y. You may not know how to write it as r is equal to f of z comma theta, right? So if that's a challenge, if you have to use the implicit form, you can do it, but then it won't look quite as nice. Like it'll be, because the maxima will have to try to plot it for every possible value of f of x, y, z, check if it equals 0. So then it'll give you sort of a rougher looking curve over here, right? By the way, if you know how to write it in explicit form, you can usually always convert it to implicit form. But implicit forms, it's not always obvious how to convert to explicit forms, right? So it's if you can do implicit form, that's preferable. Okay. And just to take a look at another explicit form. So in this case, the explicit form in Cartesian coordinates is of this form, right? So in this case, z is equal to this function of x and y, and it gives you. I mean, it looks a little bit different because here in this case we are fixing the radius. Here we are not in this case, we're not fixing the radius, we're fixing the x and the y coordinates. So that's why it looks a little bit different, but really it's the same shape, right? Okay. You want to do quick descriptions of these two?
就是在找它这个那个 implicit 的这个形式的时候，就是有点比较困难。然后我当时的想法就是把那个 x y c 用那个参数方程表出来，然后再找到它 x y c 之间的那个关系式，然后列出这个式子，然后画出这个图。然后下面这个图的话，就是它 explicit 这个形式和那个 implicit 差不多，然后这个图不太一样，就是因为我们把那个 x 和 y 它这个那个区域给规定了负5到5，所以说画出来有点不太一样，但是实际上是一样。
Okay. By the way, if I can have a TA vetting the solutions over here, that would be nice. Like maybe Zhitong. Okay, good. All right. So let's continue. And now here, the question number D asks, so we want to find a curve of this form, which lies on the surface of the cone and makes 8 loops around the z-axis as it goes from z equal to 12 to z equal to 0, right? So imagine you're on a hike, right? Imagine you're on a mountain and you're on the top of the mountain and you want to do a hike going around and round the mountain, get to the bottom of the mountain, right? So what would be the path that you would follow, right? That's the physical question over here. And in this case, so Young noted the following. Okay, so if we want the z to be equal to 0, so if z is equal to 0, because we want to go from the top to the bottom. So when you're at the bottom, then you're at z equal to 0. So then you have to satisfy this. This is the z coordinate, right? Remember in the explicit form we have in the t. Wait, let's see. Was there a parameterization? So okay, so let's just look at the question over here. So if you're going to parameterize the curve as, if you're going to parameterize the curve like this, so then the z coordinate is 12 minus ct, and this should be equal to 0 at the maximum value of t, right? So in this case, this tells us that the maximum value of t is 12 over c. Now, we also know it makes 8 loops. So 8 loops is 8 times 2 pi, which is 16 pi radians, right? So therefore, the value of b times t, so when t is equal to t max, we know that b times t should be equal to 16 pi. So that tells us a relationship between b and c. Finally, we know that the curve has to lie on the surface of the cone. And here, Young is using the equation for the surface of the cone. So the x, y, z coordinates, the x, y, z coordinates are respectively, this is the x coordinate, this is the y coordinate, this is the z coordinate, right? So, and then he plugs them into the equation of the cone and solves for a being like this. Okay, so you can find a relationship between a, b, and c as a function of the maximum value of t, right? So on the hike, you can go slower, you can go faster, right? You can take less time, you can take more time, but regardless of the speed, your curve will be the same, right?
这道题目就是我是从那个圆锥的那个顶点开始出发，然后所以说令它这个 c 等于0，然后解出 t 的最大值是 c12，然后根据这个式子，等会儿，是在哪里啊？对，根据这个式子，因为它是那个转8圈，所以说我们令那个 bt 等于16派，然后解出 b 和 t 之间的关系，然后其实就是b 和 c 之间的关系，然后再让就是在底面的时候，它那个圆锥那个下面那个圆它是半径是5，所以说 a 方 t 方是等于25，然后再解出 a 和 t 之间的关系，然后这道题目就是我感觉只能找到 a、b 和 c 之间的关系，不能，因为它们都是那个关于 t 最大值的一个函数。
Okay, and reasonable. Okay, good. Thank you. And finally, so the last part asked us to do this. So far we've looked at cylindrical polar coordinates, we've looked at rectangular coordinates, we've looked at implicit and explicit forms, and now here the question is asking to write the surface of the cone in explicit form in spherical coordinates, right? So in this case, Young's solution is over here. Over here. So in spherical coordinates, like if you think about it, so if the center of the sphere is right at the middle of the base of this cone, right? So you would like the center of the sphere to be maybe at this tip over here, right? So then what do you want? You want to fix the angle, theta, so which is fixed. So you want to keep changing the radius. You want to fix angle theta. So let's see, how would I say this? So if you're at if the center of your sphere is at this tip, then you want to allow all radii from a certain level to a different level, right? But you want to fix, and you also want to keep the angle going around in the xy plane going from 0 to 2 pi, right? Or equivalently from minus pi to pi. So phi goes from minus pi to pi. But you want to allow the radius to go from all values from, in this case, 0 to 12, right? So this looks like a slightly different parameterization. So what did you do over here?
正弦定理怎么说？就是我这里解这个就这个表达式，它其实是有关于那个theta 的一个一个函数，然后它这个表示的是这个圆锥的以圆锥那个底面的那个圆心为起点，
Okay.
对，然后到就是到面上的某一个点，然后这样子，就假设它是 r 的话，然后它这个 r 就是有关于 theta 的一个函数，就 r 的长度是有关于 theta 的一个函数。
Okay. Okay, so I understand. Let me add a few things. So okay, so this is an opportunity for a bonus point question, right? So I was thinking of something else, but Young has a different solution. So in his solution, the center is at the origin. It's at 0, 0, 0. Okay, and now his so his phi goes from minus pi to pi. So his phi's are all the way around the circle, right? And his theta goes from 0 to pi by 2. So when theta is equal to 0, then it's right at the top of the cone. When theta is pi by 2, then it's right at the bottom of the cone. Okay, and then he has to figure out the radius. He has to figure out the radius as a function of theta and phi, right? And that's fine. That's a valid parameterization. Okay, so here's a challenge for you guys. Do the parameterization as a parameterization of phi and r. Okay, so compute the angle theta as a function of phi and r, right? There are often multiple different parameterizations that can also work, right? This is a correct solution, but that does not mean that there are not other correct solutions. Okay, okay, good job. Yeah, okay, good. Let me also make one other point. So Nux noted that sometimes, like if you're trying to draw a curve, if you just use what we've taught you in class, it can look weird on maxima. And what's happening over here is, like, when maxima does not know the shape of the curve, it just uses some default values for how often to put points on that curve, right? So if it does that, then it chooses a point here, it chooses a point here, it chooses a point here, like it chooses different values of theta, and then it just joins those points with a straight line. And that's why it's looking like this, whereas what it should look like is like this, right? So the trick is, if it looks weird like this, piecewise linear, then you just have not chosen enough points on the curve. You have not used enough precision in your curve. So in that case, you should use something like n-ticks. Okay, so just choose more and more n-ticks, and then you'll get something smooth. Okay. All right. Any questions for Young? Okay. So practice making sure that you know how to use maxima. And here is a passion fruit. Have you had a passion fruit before?
Yeah.
Oh, okay.
Thank you.
How do you say this in Chinese?
这个百香果，是百香果。
百香果，百香
passion, yeah.
Oh.
百香果。
百香果. Okay. All right. So he's very passionate, I guess, about curves. All right. Good. Now I would like to spend some time on on the bonus question. The bonus question over here, which for which I'd like to invite Lertien. Actually, multiple people had inputs here, but in particular, I'd like to invite Lertien for this one. Lertien, could we have you over here? All right. So when you first saw dot products and cross products, which you may have seen even in high school, right, even before this class, you were typically taught two different definitions for both the dot product and the cross product. One of them was geometric, in terms of the lengths of the two vectors and the sine or the cosine of the angle between them. This is the magnitude. And in terms of the cross product, the direction of the corresponding vector is in the direction given by the right-hand rule, right? So I'm calling that a geometric description, because this is purely in terms of geometric objects, in terms of the length, in terms of angle, and in terms of like a certain direction given by a right-hand rule, right? We also taught you algebraic definition. So for the dot product, in terms of summation of the components, for the cross product in terms of this weird determinant, right? And a priori, it's not clear why these two definitions of the dot product are the same, why these two definitions of the cross product are the same, right? That's not clear. It's also not clear that these things are independent of the coordinate system, right? So this question proves the second part. It proves that both dot products and cross products are independent of the coordinate system. And after proving that, then you can prove that both these definitions are in fact equal. Okay, so I made some slight edits to Lertien solution, right? So this is what we'll do. Okay. Now, before I go on, do you want to repeat the facts that I said so far? So that there are two definitions for dot product, two definitions for cross product. Not clear why these definitions are equal, and not clear that these definitions are independent of the coordinate system, right?
首先是上方的点乘和差乘是有两个定义的，一个是几何的，一个是代数的。然后就几何的这种的话，就是因为它具有明显的几何意义，然后而且可以就是怎么说，就首先能看出它是独立于坐标系的，然后但是就有两个不清楚的点在于，就是第一个是不是很清楚这种几何的表达形式和代数的表达形式是等价的。然后另外一个是就是从代数的表达形式当中，我们不能直接看出这个它是独立于坐标系的，所以就这下面就先证明了第二个，就它是独立于坐标系的。
智章 Okay. All right. So actually, even before we go on, let's notice something a little bit weird in the algebraic definition of the cross product, right? So after I made edits, I made sure that everything that's a vector is boldface, is dark, and everything that's a scalar is not boldface, right? So if you look at this determinant over here, it's a strange determinant, right? The first row is all vectors. I is a vector, j is a vector, k is a vector, right? But then the a1, a2, a3, b1, b2, b3 are scalars. So that's really strange, right? Like why do you have vectors in the first row and scalars in the second thing, right? What does that even mean, right? Because if it's a vector, you should really write I as 1, 0, 0. You should write j as 0, 1, 0, and so on, right? So what does this even mean, right? And really, the way to understand this determinant is really it is just notation, okay? It is a shortcut. It is a shorthand way of writing the formal definition, which is A cross B is the vector given by the I component is A2 B3 minus A3 B2, and the J component is A3 B1 minus A1 B3, and the K component is whatever, right? But really, this determinant by itself should not make sense to you, right? Because it is it is a determinant that has different types of objects, vectors and scalars within it. So really, you should just view this as a shorthand notation, okay? So it's a subtle point, so I just want to emphasize this.
就是这个向量差乘的这个用行列式表达只是一个简化的写法，就它没有什么实际的意义吧？就因为它很奇怪，它上面一行是向量，但是下面两行都是标量，所以这只是一个就便于写然后记忆的一个写法。
形式写
形式写
这个 form 只是表达这个样子，那个规则是
就这个东西只是一个形式写法。
Okay, good. So that was one of the slightly subtle points I wanted to emphasize this. Okay, so now let's see that first of all, right now, let's pretend that we don't know that this definition is the same as this definition is the same as this definition, because you have to prove that, right? So first of all, let's prove that the geometric definitions, both these geometric definitions, do not change under coordinate transformations, okay? That if I look at this quantity, this does not change under coordinate transformations, this quantity does not change under coordinate transformation, and the direction does not change under coordinate transformation, okay? So what Leithen does is, okay, so suppose you have two row vectors. So everywhere over here, the A's and B's, we will view them as row vectors. So then after coordinate transformation, after I change my axes from ijk to some other axes given by the rows of the orthogonal matrix, then I will have A will become A times O, B will become B times O, right? Notice, by the way, because I'm thinking of A and B as row vectors. Why am I thinking of A and B as row vectors? Because later on we'll do cross products, and cross products, oh, there's a typo here, but for cross products, I want the A's and B's to be row vectors. So that's why I'll think of A's and B's as row vectors. Therefore, I want to make sure that the coordinate transformation happens as A times the O, okay? If I was thinking of A and B as column vectors, then I would have O times A, O times B, okay? So just something to keep in mind. Okay, so A and B are row vectors. After coordinate transformation by the transformation matrix A, you end up with AO and BO. So, so therefore, the AO dot BO is just the inner product, is just the product of the vector AO with the transpose of the vector BO. Then we use the usual property of transposition and use the fact that the inverse of an orthogonal matrix is its transpose, and therefore we get that the dot product between the original vectors is the same as the dot product of the new vectors, right? So the algebraic definition of this dot product, this algebraic definition remains the same before and after, right? Oh, actually, so I missed a step here. So first of all, the geometric definitions clearly remain the same, right? If you fix two vectors, A and B, their lengths are going to remain the same, their angles are going to remain the same. Therefore, both these quantities, both these magnitudes will remain the same, right? Because the lengths and the magnitudes will remain the same, and the directions will remain the same. The direction of the given by the cross product rule, for the cross product rule, the right hand rule, will remain the same, right? So it's much easier to see that the geometric definition is invariant to coordinate transformations, right? Doesn't matter what happens to the coordinate system, that remains the same. Okay. All right. Now separately, we have a different definition, which is A dot B, this algebraic definition, and that remains the same because of this property of orthogonal matrices and properties of linear algebra. Okay. So 3 things, 1 minute. Okay. Geometric definitions, both of them should remain the same because the magnitudes, angles, and the direction of the cross product vector should remain the same, right? The third thing, which is that the magnitude of the dot product vector should remain the same because of these properties of orthogonal matrices and dot products. Okay.
就第一点是，就是它的这个几何的这个公式里面，就很明显的就看出它是保持不变的，因为它的向量的模长，还有它们之间的夹角，然后包括如果是差乘的话，根据就是右手定则嘛，就它那个最后的那个方向也是一直是保持不变的。然后另外一个是它的代数形式，你要证明它保持不变的话，首先第一个是就它的写法上面就 professor 帮我改了一下，应该是 AO， 就是因为它有一个就航程列是吧，所以就需要这样。然后就是通过它这个写法的话，就通过这个 orthogonal matrix 的性质，就中间把它换一下，就通过这个推导就可以得出来它的点程是在变换之后仍然是保持不变
的。刚才跳过去是他就帮你改是行还是列的写法？
对，就是这管的是 O 乘 A 改成 A 乘 O。
就是有2种写法，如果是行写成 A 乘 O， 如果是列下来是 O 乘。就是如果是行向量的话，就是写成 A 乘 O 这样的形式，然后如果它是一个列向量的话，就写成 O 乘 A 这样子。这2种都可以。
Okay. All right. Now let's get to the last part. The fact, one of the last parts, which is that the cross product is invariant under coordinate transformations. Okay. So in this case, let's do this one a little bit more carefully. So here we have I, J, K. Again, these are the unit directions: x-axis unit vector, y-axis unit vector, z-axis unit vector, row vectors in the original coordinate system. And after rotation, let's just call the unit vector in the new x direction as I hat, new thing in the y direction as j hat and k hat respectively. So after rotation by the matrix O. So for the same reason as above, we have that I hat is I times O, j hat is j times O, and so on, right? So these are after rotation. Okay, so similarly, A hat will be, so if we call A hat as A hat 1, A hat 2, A hat 3, so this is the vector after rotation, and its 3 components are A hat 1, A hat 2, A hat 3. So what do we know? We know that A hat 1, A hat 2, A hat 3 is equal to A1, A2, A3 times O, right? And because A hat is equal to A times O, B hat is equal to B times O, so therefore we have these equations here, right? So if you're looking at A hat cross B hat, that's AO cross BO. So so basically AO is just given by A hat 1, A hat 2, A hat 3. BO is given by B hat 1, B hat 2, B hat 3. I apologize for the typo here. And then you have I hat, J hat, K hat over here. And this, so this is equal to O times, like O times the original entries here, right? Because every vector over here is just the original vector times O on the right hand side, right? And everything over here, like this second row vector, the second row vector is equal to O times the original row vector. This third row vector is equal to O times the third row vector, right? So therefore, we're just interested in the determinant of the product of these two matrices, right? And we know that the determinant of the product of two matrices is the product of the determinant of two matrices, right? It's the product of the determinant of this matrix times this one. But the first determinant is just the definition of the cross product between A and B, right? And then the determinant of orthogonal matrix is 1 as long as you're not doing an inversion, right? If it's not an inversion orthogonal matrix. So that's why you end up with the original cross product is the same as the new cross product of it, right?
就它这个之前的一点点是一个定义吧，就是经过坐标系变化之后，就是IJK 的这个算是基底变成了就是另外一个坐标系里的，就是我不知道怎么叫它，就是那个 I had 它应该叫什么？
新的坐标系，新的基底。Do you want to, just because we're short on time, do you want to do a quick summary, Zizhong?
I have some little doubt about this because that's the property that two multiplication you can split them.
Yes.
So it's not a matrix product.
Yes.
How to go?
Yeah, you'll have to actually open it out. I'm skipping some
Yeah.
steps here.
Okay.
But yeah.
Okay. So
Oh, it's not working.
no, good. OK， 所以这个的话就是完全形式的写法。形式的写法就是所有的推导都是你就把它理解成展开之后一项一项的推。然后 cross product 的话，A hat 差乘以 B hat， 那就按定义是 AO 乘以 BO。然后这里就是说，再到后面它可以写成那个乘法，一个矩阵乘以 O， 这个是你要去手动去展开就是你要去展开的理解。然后它的 determinant 可以再拆开，因为这个并不是真正的矩阵的乘法，对吧？它的 multiplication 稍微奇怪一点，所以所有这些东西就是它只是一个 shorthand 一个简写，然后你按照那个正常的那个运算去把它展开之后，去验证这个式子是对的。OK， 就是说它应该是不能直接，因为它不是矩阵乘法，所以不是说矩阵你 determinant 这边，你要去展开，然后去按照形式那种运算，硬着头皮算一遍来 check 它是对的，所以这个是写起来简单。
All right, so we're basically done with this, but there's also some comments to look at down here. So we already talked about this notation here. Okay, we'll look at this comment number 2. We've also talked about comment number 3, which is saying that the algebraic definition of the cross product should look strange to you. So we've talked about that. And then using this bonus point is using this fact that both dot products and cross products are independent of coordinate system. Question 9 has asked you to prove that that the two definitions of cross product are equal. So for a separate bonus point or bonus half point, we're asking you to prove that the two definitions of dot product are equal, and the proof is actually already in some sense hidden within this proof. It's all like it's a small part of this proof already. Okay, so just think about how you would prove that the dot products are the two definitions of dot products are equal based on the discussion so far. Okay, it's not just for 2-dimensional vectors, 3-dimensional vectors, any dimensional vectors. Cross product, of course, cross product is only really well defined for 3-dimensional vectors, except there's some weird 7-dimensional cross product that does exist. Okay, so if you're interested, you can also actually define cross product for 7 dimensions given by some complicated rule over here. Okay, but it's very exotic. It's used in some high dimensional physics. You will probably never see this ever again. Okay, so don't worry about it. I just wanted to point out this interesting fact to you. Okay, but otherwise, cross products are really only defined well in 3 dimensions, right? So coming back to this point over here, so let's look at one last point for which I'll ask. Actually, since Pei made this point, so let's give him the chance to come and explain. So Pei, could you come join us? Stay here, Lithian, because I'd like you both to you'll get some fruits. Okay, so so over here, what is the question? So the question was asking, okay, so you know, algebraically or geometrically, when you think about the geometric definitions of dot product and cross product, it's like, yeah, obviously they should stay the same. It doesn't matter what happens to the coordinate system, they should stay the same, right? But if you think of it in the following way, if you say, okay, let me define, so let me think about the dot product as a scalar function of 2 vectors, let's call them A and B. Someone's given me 2 vectors A and B, and the dot product is some scalar C over here. Okay, too small. Let's zoom in. So, so the dot product is really, you should think of it as a function whose inputs are 2 vectors and whose output is a scalar, right? And you should think of the cross product. So this is the dot product. The cross product you should think of as a vector function whose inputs are 2 vectors and whose output is a 3rd vector, something like this, right? So thank you. So if this is the case, well, you know, you can define different functions. You can define different functions which are not like the definitions you guys are used to, right? And maybe those definitions of scalar or vector functions of 2 functions, these things are called bilinear functions. These specific things are bilinear functions. So maybe those functions are also independent of coordinate system, right? And here in this example that Pei gave, and actually Sky was also involved, so all 3 are getting bonus points. But anyway, in all of these things, so here Pei gave an example of a function which, you know, we're just inventing notation now. So in this case, he's inventing a function A circle cross B is A1 B1 minus A2 B2 plus A3 B3. Okay. And the claim is that this function is not coordinate independent. Okay, it does depend on the coordinate system. So as a simple example, suppose A and B are unit vectors along the x-axis. Okay, so suppose A and B are unit vectors along the x-axis. So A2 B2 A3 B3 are 0. So then in this dot product, this circle cross product would be equal to +1, right? But now suppose we rotate the x, y, z axis so that the x-axis becomes the y-axis, y-axis becomes the z-axis, z-axis becomes the x-axis. Like let's say we just rotate. Okay, so now the x-axis has become the y-axis. So now this weird function is -1, right? So clearly in this case, that's an example showing that this function is not invariant under coordinate transformation, right? So this is why we need to worry about this thing to begin with, right? This is why we need to worry about the fact that some functions may or may not be independent under coordinate transformation. So 1 minute, quick summary.
对，就是其实这就是举一个例子，然后这个例子的话，就是对于这个运算的定义是在一个特定的坐标系里面，然后那这个我们知道的点乘和差乘的话，它就是2个相同的向量在不同的坐标系里面，它应该得到同样的结果。然后在这个例子里面的话，就是2个相同的向量，然后在不同的坐标系里面，它们会得到不同的结果。然后所以就是拿这个例子和要证明的东西做一个对比吧。
I realize this is somewhat abstract, but it's also important. It's an important basic fact that you guys should learn, and also just learning how to argue things formally, right? Now, so passion fruit for you, and for a really beautiful solution, egg fruit. Have you ever seen an egg fruit? This is from Africa. It's from Nigeria. Okay, so you should share with Pei and with Sky. Okay, so it's an African fruit. Also take some coins. Okay, so okay.
Thank you.
Yeah, the Chinese name is Gaidango. Okay. Yeah, Zidango. All right. Okay, so I know we have spent a lot of time on this. We'll maybe do one quick discussion more, and then the rest during the tutorial tomorrow. Okay. So let's do. Let's see. Okay, yeah. So let's do something relatively straightforward now, and I'll just do this myself, though I've already started awarding bonus points for these things. But for example, questions number 9 and 10 are, from this point, consequences of the discussion we've already had. Okay, so just as a quick example, suppose someone asks you to show that the cross product is independent of the definition of coordinate system. Sorry, so the two definitions of cross product are the same. So in this case, we may as well choose as an example, so as was pointed out down here, like William Vijay had pointed out, well, we can always rotate the the first vector to be exactly on the x-axis, and the second vector to be in the xy plane. Okay, so so think about it. Someone's given you two arbitrary vectors. You can always move the x-axis so that it falls in the first vector, and then you can then move the second axis. You can move the y-axis so that the second vector is in the xy plane, right? Is in the new xy plane. So it's always possible to choose a rotation matrix so that your vectors can be like A is like this and B is like this. Okay, so if you choose your two vectors of this in this format, then via some calculations, now here in this case, Chanfei went all out. He used very general vectors and did all these calculations and showed these are equal, right? But if you choose simpler vectors, then those calculations can be simplified. So for example, if you choose both A and B to be in the xy plane, the calculation is a bit simpler. And if you choose the second component of A to be 0, it becomes even simpler, right? So that's an example of how showing that the cross product is coordinate independent, the proof becomes a lot simpler. Okay. Now, just to finish this discussion of question 9, and we'll have to do question 10 and the other question 8, question 10, question 7, all of those things we'll have to do tomorrow. Let me point out opportunity for a bonus point question. So in this case, who was this? Oh, I think Lerthian pointed out that, okay, so you can rotate A and B so that A is along the x-axis, B is in the xy plane, but finding the rotation matrix is not obvious, right? It's not obvious exactly what that matrix will be. That's true, it's not obvious, but it's doable, okay? So bonus point opportunity. So given an arbitrary vector in 3 dimensions, A, and another vector in 3 dimensions, B, find a rotation matrix that will move the first vector to the x-axis and the second vector in the xy plane. Okay, that's the bonus point question. Is it unique? Okay, or are there more than one? So think about this. Okay, all right. So we're basically out of time as usual. Short class on Wednesday, right? So we're done. Oh, I see. The TA is asking me to ask you that some of the computers have connection issues, like with Maxima, or network connection issues. So can you raise your hands if your computer has a network connection issue? Okay, so that row over there, huh? Okay, fine. So, and by the way, just out of curiosity, how many computers had problems with Maxima yesterday? Can you raise your hands? Maxima. So, can you raise it higher, just so that we know? Okay, so we're assuming that everyone else's computers worked, right? This is important because we want to make sure that the things work. Oh, let me also point out, I did a quick survey asking about so the midterm, I would like to hold a longer midterm than then just the usual 90-minute midterm that the other exam other session will be holding. So if you're not available before or after, please come talk to me. Please come talk to me after class. Okay. I would like to ideally hold something like maybe 2.5 hours even. So I'd like to see which slots are available, which slots are not available, and try to get something to work out. Okay. So Jiajie, Jinpei, and Shujin, please come talk to me. And everyone else, please also fill in. Like if you're not available in either before or after the Thursday slot, so please come talk to me as well. Okay. All right. Class is over. See you tomorrow.